it's a pleasure to chair this, say, night session. So this is the last session of today, Monday. So we will have two speakers, and the first speaker will be Tao Chen, and the second speaker will be Anastasios Santiris, and Tao Chen will speak about dynamics of generalized tangent maps. So please, it's your turn.
Okay, thanks to the organizer to having me. I'm really glad to be here again. This is my second time to be at the TCD. So I really appreciate the organizer's effort to have such a great event. Today I'm trying to talking about the joint work with Linda King on the dynamic, in particularly the parameter space of a family of the meromorphic function. In particular, will be the generalized tangent map. As Lassa just talking about earlier today, so when we're talking about the dynamic of the holomorphic map or the meromorphic map, so the dynamic really depends on the critical value or asymptotic value. So even though a lot of overlapping, I would love to start with the definition of the asymptotic value. Why is not okay? Hopefully it's moving. So a value is called the asymptotic value if there is a path. Basically, this path is the infinite path, but the image of the path and the f goes to the v. Here, the v could be infinity. So it could be finite or it's just infinity. Let V be asymptotic value of the f if there exists neighborhood of the V and unbounded simple connected set of U such that U is universal covering of the puncture neighborhood of the V. Then we said U is asymptotic tract. Usually, if the asymptotic value discrete, so basically you can always find this kind of neighborhood. So the most well-known entire map will be the exponential map. So that will be normalized either as e to the z plus key or the lambda times e to the z. So for this map, there have two asymptotic value will be key and infinity. If they are normalizing another way, that will be 0 and infinity. There are asymptotic value, asymptotic track basically will be the left and the right half plane. Another well to investigate meromorphic function will be the lambda tangent z. This family also, each map in this family also have two asymptotic value, the positive or negative lambda I, and their asymptotic track will be, I'm sorry, asymptotic, asymptotic track will be the upper or lower half plane respectively. So the parameter space of this two family has been well investigated. So there are many results about this. I just summarize some of them. So Rampe and Schleicher has work on the bifurcation of the exponential map. They show that the bifurcation locus of the exponential map is connected. Also, each hyperbolic component is unbounded. In particular, it's each boundary, the boundary of each hyperbolic component is unbounded Jordan curve and tend to infinity in both directions. This is the the parameter space, the computer generated picture. And for the tangent map, since the tangent map is all the function, so if you have a cycle z1 to the key, then the negative of all the point is also a cycle, in particular also with the same multiplier. So in another word, this two set either will be in the same cycle, or these two sets will be in the two separate cycle. So we denote as the omega key either have two attracting cycle of period key, or they have one attracting cycle of period 2 key. We can show you also the parameter space of the lambda tangent of z. As we can see, the omega 1 here, the white region omega 1, that basically is the region of the lambda, such that this region here, will be the lambda such that the map has two attracting fixed points. And the omega prime is this blue region here, will be all the lambda such that it has one attract cycle of period 2. And this blue bubble here, the omega 2, will be the lambda such that the map has two attracting cycle of period 2. And below that, this red region will be the lambda such that the map has one cycle of period 4. In particularly, they meet at a point is the lambda equal to the pi over 2 times the I. In particularly, this point satisfy if I multiply by I, the multiply by I, that's basically is the asymptotic value. So that asymptotic value is pi over 2, that's a pole. So that's mapped to infinity. In particular, as this parameter, the asymptotic value of this map is pole. So look like this picture here, look like all the components other than omega 1 and omega prime, 1 prime is bounded. So in fact, this is what they proved. This is proved by King and Cotes. They proved that omega 1 and omega prime are unbounded and the other components are bounded. In particular, they trying to locate each of other components, and they show that the component of the omega key and the omega key prime will meet at each solution of this equation. Basically, that trying to say is the asymptotic value of this point will be the a pre-pole of some order. If the period is a key, then the order is key -1. Okay, so we can see the parameter space of these two family kind of, even though they share some similarities, such as each hyperbolic component is simply connected, but they also have some difference, such as we know the parameter space of each component in the parameter space of the e to the z, that's always unbounded. But on the lambda of the tangent z, almost all the components are bounded except the omega 1 and the omega 1 prime. So later, Fujila and the key.
Sorry, somebody is speaking with
Oh,
you.
sorry, I saw it's a question.
So a host can help with us.
Okay, Fujila and King later considered that M infinity is a family of the meromorphic function of the finite type. In particular, infinity is not an asymptotic value. Usually, this kind of space is finite many-dimensional space. So they want to consider one-dimensional slice of this family. So they call the dynamical natural slice. What they're trying to say is because if you have multiple singular value, so the dynamic of most of the singular value is fixed except one of them, and denoted by V lambda is called the free asymptotic value. we see a component of the parameter space for which the free asymptotic value is attracted to a new attracting cycle is called a shell component. The main reason is the computer generated picture. Basically, this component always look like a shell. We denote the omega key basically is the attracting cycle is the period of the attracting cycle is the key. Okay, so they prove they have many results. One of them is they trying to characterize the shell component. First is each shell component is simply connected. Second, each component in the omega 1, that means the component who has the attracting fixed point is unbounded. And on the boundary of the shell component, there exists a lambda such that the V lambda is a prepose, so they will map to infinity. So this kind of lambda they call the virtuous cycle parameter. So we would love to see more about. In this paper, they also have some propose some question and conjecture. So as we know, the omega 1 is unbounded. What about the other component? That means the component who has the attracting cycle of higher period. So they conjecture that each component of the omega key is always bounded if the key is greater or equal to 2. And another thing is they already show on the boundary of the shell component, you have a virtual cycle parameter. But the question is that possible the virtual cycle parameter is a buried point of the hyperbolic component or the shell component? In other words, for every parameter, is that possible is always be on the boundary of a shell component. Linda and me think about the generalized Nevanlinna family. So basically we consider the family, this consists of all the map will be P critical point and R asymptotic value. Here we count with the multiplicity. We can characterize this map as a Schwartz derivative is R minus 2 polynomial. I just want to note that if we consider the map equal to e to the z, this map has 3 asymptotic value will be 0, 1, infinity. However, this is not the map in our family because the 0 and infinity has infinite many asymptotic tracks. So that's the thing. So when we consider the asymptotic value, we also count with how many asymptotic tracks that it have. Okay, for this family, we show that there are no the lambda, the virtual cycle parameter couldn't be a buried point. So every virtual cycle parameter will be, there exists a shell component such that the lambda in the boundary of the shell component. The main idea of the proof is because on some direction, the map is super contraction. So we are able to find at this point nearby, I can find the parameter such that you have a attracting cycle there. Okay, we want to consider more specific map here. We call it the generalized tangent map. So this will be the lambda tangent P to the z to the q. If the p and the q, both of them are 1, this is basically the tangent map. So we will love to the p and the q, and unless one of them is greater than 1. Of course, this map has a critical point. The critical point will be the solution of this this equation. They have infinite many critical points. Fortunately, the critical value is only 1. Of course, that will be a super attracting fixed point. Since that's a super attracting, so we have the attracting basin, and particularly also we have the emitted basin. So for this map, the asymptotic value you have 2 will be positive or negative I power p times lambda. We know if the p is even, it only has one asymptotic value. If you have 2, the p is odd, you have 2. But if the q is even, so you only has the function is even. So this 2, the orbit of this 2 will be the same. But if both p and q are odd, then this function is an odd function, so their orbit always be, the asymptotic value always be symmetric respect to 0. So in another word, so I only need to look at the orbit of one of the asymptotic value. Of course, we know that the dynamics of this map basically will depend on by the orbit of the V lambda. Okay, we will basically work on this, the dynamic of this map. The first thing we have is we have the similar dichotomy that the Julia set of this map is connected if and only if the V lambda is in the emitted basin. So the main idea basically the similar as we did for other map if they don't have much asymptotic value, or I'm sorry, for the rational map if they don't have much critical point. Basically, we show that this map doesn't have the Hermann ring. And another thing is this 2 asymptotic value will never be in the same component other than if they fell into the emitted basin. So this in some way that says the dynamic of this map is nicer because they have the similar dichotomy as the rational map of the polynomial of degree 2. Okay. We also want to consider the parameter space, in particularly where the asymptotic value will be attracting by attracting cycle. So first, because we have the 2 things, either we already have the 0 is super attracting. Either this point will be attracting to 0 or they are attracting to something else. So if they are attracting to 0, we call that capture component. So that's trying to say the V lambda is attracting to 0. Then we can divide that into the C key, where C key is we are trying to 0, we want to measure how many steps they fell into the emitted basin. So then for the shell component, basically is the V lambda is attracting to the non-zero attracting cycle. So if there's EP and Q is even, so we see the S key will be consist of you have the attracting cycle of periodic key. If P and Q is odd, so they will have to distinguish them. So either they have a attracting cycle of the 2 key, or they have 2 attracting cycle of periodic key. So what we're trying to do is trying to characterize or trying to understand more about the shell components and the capture components. Before we do that, I think it's better to show you a picture. So this is a parameter space of the lambda tangent z, a tangent square of z to the cube. So all the green region, like here, all the green region are the like here are all the capture components, and all the region in other color will be the shell component. So like this yellow region here, those will be the parameter such that the map has a fixed attracting point. And like this blue, they will have the attracting attracting cycle of the period 2. Of course, this space is symmetric. It's a symmetric space, and also look like all the component here. The yellow region is unbounded, and the rest of region look like it's bounded. So what we try to do is trying to convince this is a picture, and also we trying to get some complementary information about this picture here. First things we did is the capital component of C0. That C0, I just remind you, the C0 basically means is the attracting, the asymptotic value landed on the image basin. So it itself in the image basin. So if we add 0 there, it's simply connected. And the other components of each C key is simply connected and also contain a unique solution such that the V lambda landing on the 0. So the proof is the proof of this capital component is simply connected. It's not something new. So mainly we use the quasi-conformal surgery. So the idea has been used by Roger for the polynomial and for Jella and Girajo in the entire map. So we adapt it in this meromorphic function. And for the central component, the central component means the in the middle here, the region here, which the asymptotic value in the image basin, we can see a little bit more. First, this central component has a definite size. There is a disk, doesn't depend on the n. I mean, just depend on the q will be inside of the region. Second, we using the Boucher map, we can find a covering map from the central component to the puncture disk. The similar as the Mandelbrot set, we can the Duadian-Harbor construct a conformal map from the outside the Mandelbrot set to the outside the unit disk, so we can define the external ray. So the similarly, since we have the covering map from this domain to the puncture unit disk, so we can also define the internal ray of this parameter space. So we prove that any periodic rational ray, I mean periodic means under the Z to the PQ, will landing at either a parabolic point, a parabolic parameter. That means this parameter, the map has the parabolic periodic point. Or you have the Mitrovici point. That means the asymptotic value will landing on the period cycle. Of course, that will be a repelling cycle. So I want to see one thing is a little bit different with the classic the external ray of the Mandelbrot set. We know Mandelbrot set, so the period array always landing on the parabolic point, but here they could landing on the Mitrovici point. The main reason is for this family, the asymptotic value doesn't has to be a midpoint. So as well, the meter for this Mitrovici point, the V lambda could be exactly in this cycle. So this is basically a little bit different from the classical quadratic map. And also we also look at the shell component. For the shell component, The set of the S1 consists of 2Q unbounded simple connected components. And for other key, so each component, each parameter such that the V lambda is equal to infinity, you have 2 PQ components there. So basically this is trying to locate each shell component. In particularly, we proved that all the components other than this this component who has the fixed attracting point that's always be bounded. So this is basically in this particular case, the conjecture from Fadela and King is true. For the further work, we will allow to see more about its meromorphic function if only has 2 asymptotic value, and also we also look at the meromorphic function who has more critical value or asymptotic value. So I should stop here. Thank you so much for your attention.